was going to say, and I don't know if you heard me or not, there's a change in plans, unless today collapses, in which case I'll change in plans. I'm not going to do anything on Wednesday. Next week we have a full week. We have Monday and Wednesday. So Monday I will be doing 11:10, and Wednesday I'll do 11:12, and that's us finished. So 1 day in each, and that's us covered. I think that'll work well. So let's see if we can get some more technology to work. That looks okay. This is the topic for today. There is no homework this Sunday. There are no online tests this Sunday. So you won't have anything along those lines, but I would strongly suggest that you do this sometime, this section. Otherwise, you'll get overwhelmed with homework and getting ready for the final. So if you can find some, little chunk of time or a couple of chunks of time during the pandemonium that's befalling us all, that would work. Okay, so here is a power series. And I am telling you that this fraction, this rational function, is equal to the power series n equals 0 to infinity x to the n. I am telling you, that infinite polynomial here is the same as the fraction 1 over x. And this one here is equal to that power series. And we are going to use these two as building blocks to find the power series for other fractions, other rational functions. There's about 5 out of the 10 questions are going to be of this type. And the key to doing these is essentially substitution, which means you find a way of taking your fraction and using one of these two with some substitution to get its power series. To give you an example, if I wanted to know what the power series for the fraction 1 over 1 minus 3x, what I would do is I'd say, oh, that guy kind of looks like him. It's not exactly the same. There's a 3x here. That guy there is a 1x. I want you to think of this x here not so much as an x, but as a placeholder, right? A place where you can put stuff. Now, if you replace this x with 3x, wouldn't this be the same guy? So you take its power series and you say, okay, what would that be replaced by? It would be replaced by 3x. And so the power series for this fraction would be that guy. Does that make sense? Substitution. Now, there's a little bit of style points involved. That just means make it look nice. And normally when you do a power series, one of the things you should really make sure that you do is separate it out so the x, whatever that x might be, is on its own, right? So it's 3 to the n, x to the n. Now, there are a whole bunch of questions, 1, 2, 3, 9, and 10, where you do this kind of thing. They also almost always tell you to find the interval of convergence or the radius of convergence, or sometimes both. Will you ignore that question? Right? You've done radius and interval from another section, and if you have to keep doing it for every one of these questions, you're going to double your workload for no benefit. And that means I have to go back in and fix your scores on your homework. So you might do everything I ask you to do, and WebAssign's only going to give you 70%. I'll go back in and turn it into 100 when I get around to it, right? So ignore, unless you feel you want to, I guess that's possible. Ignore the bit where you take the answer and find its interval and or radius of convergence. We got that? Now, let's take this guy and make it an x squared. and we'll keep the bottom the same. So I now want to find the power series for this fraction. Well, first thing you do is you split it into two pieces. Anything on the top. So if the top was x cubed, 5x, things like that, put it on its own. The piece that's left should have this basic shape, 1 over 1 take away somebody, right? That's the piece that you need, because this piece, we've already done it, right, can be turned into a power series by substitution. So what we're going to get then is x squared, and this guy turned into a power series. And I already know what it's equal to, so I'll just write down the simplified version, which is that. And we're still on style points. Power series must have the x's on their own, check. Second rule about power series is you can't have anything outside the sigma. They must all belong inside the sigma. So you can bring that x squared inside. And you're allowed to bring in numbers and take out numbers in sigmas. You're allowed to bring out x and x squared inside and outside. You're not allowed to bring inside an x to the n, right? X to the n's can't move. But an x squared can come inside, it's allowed to. And then if you look really carefully, you can do a little bit of cosmetics. Can't that x squared and that x to the power of n be combined into a single power of n? And I'm just going to ask John, because I'm going to ask somebody else the next time, right? John, what would you get if you add x, if you, oh, I almost said the answer there. What would you get if you multiplied x squared and x to the n? What single power of n would you get?
A single power of n would be 2n, right?
Not 2n, that's what you'd get if you took x squared and squared it. X squared times x to the n.
X squared. 2 plus n?
Yep. And I'll just put n plus 2 because that looks pretty. Yeah. Now, if that was x cubed, wouldn't you have n plus 3 and so on? There's your power series for this fraction. Right? There's your x squared, that guy. Substitution to get the power series. Bring the x squared in, then make it pretty. A lot of people can go from this line to that line without needing the one in between. Right? They just say, oh, 2 more powers of x. Okay, give that 2 more powers, x plus 2. Right. Now, next fella. 1 over, excuse me. Try that again. 1 over 1 plus 4x. Now, that has a 1 plus 4x. It looks just like this guy, right? 1 plus x. The difference is that's not x, right? That's 4x. So what you do is you substitute the x to the n with a 4x to the n, right? Instead of 1 plus x to the n, you've got 1 plus 4x, you see? Substitution. Instead of x, 4x. And then you do some style points. And you have 4x to the n can be split up as a 4 to the n, x to the n. So there is a power series. Now you can put some guys on the top. How about a 2x on the top? Oops. Jumping ahead here. First thing you got to do is do 2x times that guy, right? So you split it up as 2x times this guy. We've already done that guy. Here's a power series. And then let's bring in that 2, right? Bring it in here. So I'm going to put the 2 there, a -1 to the n, a 4 to the n. And when this x comes inside, can't you join it with the x to the power of n that's already there? And x times the x to the n, you now have one more power of x, x to the n plus 1. And that's you finished.
So this might be something I'm totally missing here, Bob.
Mm-hmm.
Where's the -1 to the n coming from?
It comes from you're told that 1 over 1 plus x has that -1 to the n. We just tell you that that's true and you just use it. You see it here? 1 plus x
Yeah.
is this guy.
So
That's where it's coming from.
You went from the one at the top to the one at the bottom?
Yeah, because in this question, it's 1 over 1 plus 4x.
Oh, okay, okay.
Which means use that guy. If this had been 1 over 1 minus 4x, we'd basically be using the top guy, right? Right. 1 plus 4x, use the bottom guy.
Yeah, I was just wondering.
We're good?
I get it now.
Right, right.
Good.
Let's up the ante then. Let's suppose we do 3x over 1 take away x squared. And I'd like to get the power series for 3x, 1 minus x squared. First thing I'm going to do is split it up into a fraction that looks as close to these guys as I can. Do you see in this case, it looks like 1 minus x squared, right? 1 over 1 minus x squared, this guy. Right, so Eric, can you hear me?
Yes, I can.
Right, putting you in the spot here. Right, this guy is 1 over 1 minus x squared. Should I be using the top or the bottom for this fraction? Should I be using this information or using this information? Top or bottom?
The bottom.
Okay. Well, let's see why let's see the feature. Do you see a 1 take away x squared here? See that guy there? The crucial thing to look for is that negative. Do you see this guy has got a negative in it? And this guy doesn't. So this is the guy I'm going to use. Do you see why we use that guy? Right. 1 minus, here we go. 1 minus somebody. 1 minus somebody. Don't think of that as an x anymore. Just think of that as a something, right? 1 over 1 minus something. 1 over 1 minus something. Do you see it?
Yeah.
Right.
Okay.
Now, if you think of it like that, we're going to do this guy. Then you're going to get sigma n equals 0 to infinity. When this guy is x, that guy is x. When you have x squared, this guy becomes x squared. So to get from here to here, I'm basically replacing the x in, I guess I'll give them names, formula A, which is this guy.
Mr. Robinson,
Yes.
can you please not write in the top right-hand corner of the paper? Because when I try to go back and look at the video, your picture is right there and I can't move your picture.
You mean my good looks are distracting you?
No. It's just I can't see what you write because it's in the top right-hand corner.
I get you, right.
Yeah,
it looks good in my version, but looking good in my version isn't any good to you. I understand that. Is it just about here that I need to worry about? Is it like it's half of it? I mean, I'm just trying to figure out what you see.
Like right where the X squared ends.
Right. And does that go all the way down the side or just to the top right-hand corner?
Just at the top right-hand corner, like down to where your arrow ends.
Right. So if I kind of little notes to self, if I keep
Further to
away
your
from
left.
here, right? If I keep away from this bit here, will be
Further-
good.
A little bit further to your left, like a half an inch.
If I go
Yeah, that's good.
right, so keep away from there. Got you. Do you see it live, even if you don't see it in the video?
I see it now. I just don't see it in the video.
Gotcha. Okay, that was helpful to know. Okay. How far down does the video disappear? Do you tend to see the last line?
Yeah, it's all good. I've never had a problem with the bottom.
Just that funny little corner,
Yeah.
because my
Now-
face goes there.
Now that you move your paper over, I don't think it's gonna be a problem.
So sometimes when you're making like last second notes, like as you're finishing a problem and then you move the paper over, I have
Yes.
to put the video into slow motion
Oh, 'cause
just to catch that last tiny little bit. Like if it's like, was that X to the third or was that X squared? So I have to put it like 0.25 speed and just have to stop it at the perfect moment.
Are you saying I should be writing in slow motion? Okay. Right, we've got the 3x, we split it as a fraction. We recognize that this guy here is like formula A. So when I write replace x in formula A, and just for completeness, I'll finish that with an x squared, with the x squared.
Uh,
What you've
That's why I
now
was so
got,
confused. So I didn't even
Because
know those
isn't
were
it-
formulas. Oh, sorry.
oh yeah, these are two formulas. These are two building blocks that we're going to use pretty much all the time today. So we have A and B. So what we have here is we might be getting a feedback of someone. It sounds like a television in the background, but it could be somebody in an office. So if you know it's you, you may want to go on mute. I don't know if you can hear it, but I can certainly hear it.
I can hear it. I was getting ready to say something.
Okay, we good? Perfect, whoever it was has figured it out. So we have 3x, and this guy is going to be turned into x squared raised to the power of n, x to the 2n. And all I'm doing really from this line here, where my finger is, to the end, is getting everything into a single sigma. So x squared to the raised to the power of n gets me x to 2n. If you bring this guy inside, which you're allowed to do, you get that. Again, I'm probably putting in more lines than you need. You get this guy, and this combined to 2n plus 1. And that's us finished. The power series for this fraction is that guy. Just because I want to, I'll show you a few terms of this power series. So this is a fraction, a pretty weird looking fraction, right? It's got problems at 1 and -1. And when you do the interval of convergence, it will tell you you can only use values inside -1 to 1, right? So don't go anywhere else. It will basically tell you that. But for this fraction here, if you plug in 0, you get 3x. If you plug in 1, you get 3x cubed. Then you get 3x to the 5 plus 3x to the 7 plus 3x to the 9, forever. Do you see you're basically just doing the odd powers of x, but 3 of them? And that generates that fraction. Now, if I had time, and you can do this if you want to, plug about 5 or 6 of these guys, right? 1, 2, 3, 4, like those 5 into Desmos, and then plug that guy into Desmos, and you could see how good a fit they are, right? You'll see they're not a perfect fit, but they'll be a pretty decent fit. And if you put 20 terms in, you probably wouldn't be able to tell the difference in Desmos, right? There might be 0.1 out, but that's so small that you wouldn't be able to detect it, right? So this works. This basically can take any function, and we're dealing only with fractions right now, and convert them into infinite polynomials, which we call power series. And the process that I'm doing here is taking this guy and figuring out how to find its power series by just using two pieces of information that we are just considering as formula that you've been told are true and work. So we've been told that 1 over 1 minus x is this infinite polynomial, this power series, and 1 over 1 plus x is this guy. In fact, technically speaking, I only needed to give you this one. And if you replace the x with -1, you'd end up with that guy. But it's just easier to show you both.
So shouldn't you
far.
have the summation n equals 1 to infinity next to the 3x divided by 1 minus x squared?
No,
Wouldn't
that
make
in
sense?
fact is not, that is it. That is the function. It is not a sigma. This is the power series. That's the function that we made a power series of. So this
So are
guy
you plugging
does not
the
have sigma.
are you plugging 1, 2, 3, 4, 5 into
Oh,
3x?
I'm actually plugging in 0, 1, 2, 3, and 4.
to the
Because
power
it's sigma,
series?
yeah, into the power. So if you plug n equals 0, you'll get 1 here. If you plug in 1, 2 lots of 1 plus 1 gets you 3. Do you see it's only the odd powers that get generated by this particular one?
I thought you were plugging in the 3x divided by 1 minus x
No,
squared.
no. I'm using this guy, just doing 0, then 1, then 2, then 3, and finally 4.
Thank you.
Any other questions about these? Because we've got a lot more of these to look at, but it's a good start, right? Okay, let's move on. I think there's a guy at the bottom. I might as well pick something. No, okay. Let's make a very small change that does a lot of damage.
Hey, Professor, can I ask you a slightly on-topic but off-topic question?
Go for it.
I have a friend of mine who's taking Calculus 2 right now.
Integration, right?
Yeah. When you were a student, which of like the different calculus classes was like the hardest for you?
Trig was the hardest for me. 142. Mostly because of those 101 identities you had to remember, which I could never remember because I have an atrocious memory. The way I survived that sounds stupid, but it works for me, was I memorized how to prove a trig identity. So in other words, I would just create them when I needed them rather than trying to memorize them, which is not a very good way to do it. But that's the workaround I finally got. I would be no good at a language, because to me a language is, here, memorize 10,000 words and know where you put them to make sentences, because I can't see any logic to them. And anything that involves just memorizing was bad. So for me, it was trig. I never found calculus too bad, because for me, calculus felt sensible, because I didn't need to remember really that much. I mean, most of what you do in calculus is process and a few formula, but the formula themselves, like the product rule or integration by parts is a process. And Calc 1, differentiation is mostly formula, right? Product rule, quotient rule, chain rule. Integration's more process. Integration by parts, I guess, is an exception. Calc 3 was fun. I just like Calc 3, Calc 4, because they were just, I like math. So,
yeah,
maybe not the one you were expecting me to see, but trig is the one I had trouble with.
I don't even know why they call it calculus. They should just call it like advanced algebra.
Oh God, yes. You've all finally dawned on you that in calculus questions, or any kind of calculus, 10% is the differentiation, integration, calc stuff, and the other 90% is algebra, either making it look pretty or changing into form that you can use.
I have a tutor for math, and I always love their interpretation about the difference between Calc 1, Calc 2, and Calc 3. They said Calc 1, Calc 2 is is the graph looks like this. But when it goes to Calc 3, the graph looks like this.
Well, that's because they introduced Z. Okay. Right. Okay, let's look at this guy. Sometimes the most innocuous looking fraction causes the biggest trouble. Now, you might be looking at it and say, well, it looks like A, which it does. So don't I just like stick a 4 here and call it good? No. You have to do something that is at first sight quite artificial, but you need it. For to be able to use either of these two formula, these two power series, we need this guy here to be 1 take away somebody or 1 add somebody. I can't do it with 4 take away someone or 4 add someone. So you pull out a common factor of 4, which isn't a normal thing to do in an expression like that, but nonetheless you do it. Now you see that guy gets you 1, and are you okay with this being negative a quarter? Because if you pull out a thing and you multiply it back again. Now what happens is that you now get 1/4 times 1 over 1 minus a quarter x. Okay, Calvin, you're getting thrown in the hot seat here.
Okay.
See this guy here, the 1 over 1 minus a quarter?
Mm-hmm.
Which one of these two formula do you think I'm going to use with it?
I want to say that you're going to use A.
And you're right. Why? What made you think A?
Just looking at the fraction, just it looks almost completely similar to A. 1 minus x, but there's a 4th in the front.
Right, and because there's a 4th in the front, when we write down its power series, sigma n equals 0 to infinity, instead of putting an x, because there's an x in the front, don't we now put a quarter x? You see that? That guy? Replace the x with a quarter x. Now, back to algebra.
Wait,
Question.
real quick, which part did you replace with the quarter x?
I replaced this x, right, this x here, with a quarter x.
Yeah. Okay, you just plug that guy in.
Right, because that guy used to be x, and when it's x, you get an x here. But when it's a quarter x, you get a quarter x here. If that was x squared, wouldn't I have an x squared here? And so on and so forth. Whatever this guy, the minus guy is, that is the same fella. So if that was a half x, this would be a half x in here. Right? Here it's a quarter x, so a quarter x there. Now, style points. This guy can be called 1/4 to the n, x to the n. Right? Just separate them out. Are we cool with that? Now, I don't want anything hanging outside, even something innocuous like a quarter. So I'm going to bring it inside. And you probably don't need this line, but I'm putting it in anyway. Can you see that the 1/4, the extra 1/4 I come in, can be joined to the guy I've already got? And now we've got 1/4 to the power of n add 1. Do you see that guy is there? Are we good with that? Now, I like this answer, but just in case WebAssign doesn't like this answer, that's the equivalent to it. If you're wondering how did that happen, let me show you over here. If you take 1/4 to the n plus 1 and you multiply it by x to the n, the xn doesn't matter, it stays put. But this guy can be thought of as that guy, right? Essentially, split it up. Now, isn't 1 to the power of n plus 1 just 1 times 1? It's 1. And then bring them together. Are you comfortable about how this guy became that guy? It's that 80% algebra thing, right? You're doing algebra more than you're doing any other skill in calculus. We cool? Let's try, well, let's try and put as many different things together as we can. This is a version of question 3. We're going to have an x squared on the top. We're going to have a 16 plus x to the 4 on the bottom. So we're really getting into the ugly ones now. And I'm going to take it really slowly. First thing is, just pull out that x to the x squared so that I've got a 1 over guy. I want a 1 over so that one of these two guys will work. And then I look and I say, oh, darn it, there's a 16 there. I can't have 16. So what I'm going to do is pull out 16 as a common factor, and that leaves me with 1 plus 1/16 x to the 4. I think I'm kicking over to that corner I should stay away from, right? Are you okay with pulling out 16 and leaving 1 plus a 16th x to the 4? Now, that guy can come out, and so I've now got x squared over 16 times 1 over 1 plus 16 x to the 4. So far, so good. That's the original fraction, which looks quite nice, but this is how I had to change it. And I had to change it so I can use either A or B. Who have we not? Natalie, are you with us?
Yep.
Okay, you're getting the shot this time. A or B, which should you use in this fraction here?
B.
Are you getting used to the fact if it's a plus, use B, and if it's a 1 minus, use A? Because that's essentially the trick, isn't it? 1 plus, use B, 1 minus something, use A. Now, the something is this horrible mess here. 1/16 x to the 4. So here goes.
Professor,
Yes.
Just real quick.
Mhm.
It might be because that I'm seeing things. In that second part, the x squared times 1 over 16, 1 plus
X to the 4.
x to the 4. Is there a parentheses encompassing the end of that x4?
There should be.
Make sure. Okay.
Yeah, should be. I just ran out of space to put it, I think. So this guy here, this 1/16 x to the 4 guy, he's going to be this x that goes here. So it's going to be -1 to the n, but instead of x to the n, 1/16 x to the 4 to the n. So whatever this ugly guy is, put him in here and raise him to the power of n. Right, so 1/16 x to the 4 goes here, raise it to the power of n. And from this point onwards, we're going to try and make it look pretty. This guy can be split. He can be split as 1/16 to the n, x to the 4 to the n. Are we comfortable about these two guys being split? Right, 1/16 to the n, x to the 4 to the n, right? Nothing else has changed. Now,
You can't make that just x to the 4n.
exactly, that's exactly what I'm going to do.
Okay.
I'm kind of putting in all the steps that typically I wouldn't put in, but in this case I will. And just like you said, x to the 4n, right? Is this question fixed, or is there some more stuff to do before this is finished, I guess a better word.
You asking somebody individual or just anybody?
I think this is an open go for it if you feel comfortable about it one.
Throw the x squared and the 6 over 16 into this. You got to throw it in there somewhere, right?
Yeah. So I'll just put these two guys here and I'll throw it in here. Kind of chucking it in the middle. Right. We're getting darn close to, you know, being finished. It's all a matter how do you combine certain things. That's an N, by the way, not a 2. Right. Do you see this 16th in the bottom? Right. I know there's an X squared there, but you see this 16 in the bottom? Isn't it really 1/16? So you get it. You get another 16 into the mix. Are you happy about 1/16 to the n plus 1? This 16 joins that guy, and now you've got 1 plus n plus 1 of them. And this x squared times that guy gives me 2 more powers of x's. And there is our answer. But in case WebAssign is being a pain, a 1/16 can come downstairs. Oops, that's an n plus 1. Like that. So we have a power series for guys that look like that.
So is that as far as you go with that? I mean, you
Can't
don't,
do any more. That's it, finished.
do we have to figure out later if it diverges or converges, or does that even matter?
It might, and I'm looking at them right now. It probably is going to ask you to find the interval of convergence, but you would do the ratio test and all that good stuff. But we're not doing that question because you can do that. You know, you've done it 100 times. It's just going to slow you down. I think I should try one more of these. I'm trying to find some that's a little bit different. But I think we've covered all the good stuff. Okay, this one. This one is similar to question 9. It's that guy. $13 is the problem again. Pull out 13, and now I have 1/13 x. Are we comfortable with that guy? Right. The bottom is 13, 1 minus 1/13 of x. I'm now going to split it as 4/13ths and a 1 over 1 minus 1/13 x. Okay, Thomas, you're on. Should you use A or B for this power series here? The 1 over 1 minus 1/13 x. I'm waiting to see your chat. Yep, you're correct. Thomas said use A, and that's the one we're going to use. So it's going to be 4/13ths. That guy is sigma n equals 0 to infinity. And instead of x, you put whatever whatever is there. And in this case, 1/13 x. And now it's algebra time. But a lot of the things you do, you tend to do the same thing over and over again. So if you want to separate this, you do that.
Professor,
Yeah.
what
Yes.
happened to the how did it turn into 4/3 from 4/13?
Let it turn back again.
Okay.
I'm too busy. I'm thinking of down here what's going to
That's
happen.
awesome. That's
Yeah.
awesome.
Yeah, you're used to me now, right, guys? You're used to me. Okay. Are you happy about this guy splitting into these two pieces? Right. So what's going to happen is I'm going to bring this inside, right? And let's see if we can cut some corners here. That 4 is really the only 4 in town. So I'll make sure I separate it by putting a multiplication sign in, or if I want to do overkill, put a bracket around it. And then this guy joins this guy. You're now going to have one more, and then you have an x to the n. And if you want to, and I think in this case, it actually kind of makes sense. Would you agree in this situation, that's a little bit cleaner to see the power series? And the reason I'm worried about that 4 and trying to emphasize that it's just a 4 on its own is that if you're not careful and you just write down 4, it sometimes bleeds into the 13th and becomes 4/13th, and that's not what it is, right? It's just a single 4, because the 13 has n to the 1 attached to it, right? It's n to the 1 times. It's a, it's a big expression.
So can you connect it to the x over n?
Only in this, you don't. Yeah, you got to be, the way it's written is okay. Mathematically, that means this guy times 4.
Yeah.
You can't do that because that's totally different meaning, right?
Okay.
Not that you would
got
probably ever want to do that, but you can do that. This
Okay,
is
got it.
okay. Agreed?
Got it. Thank you for that clarification.
Not a problem. We are through that list there. Now we are going to look at just a couple of questions. And that is, how do you find power series for functions like 1 plus x, the natural log of 1 minus x, or that guy, the inverse tan of x, right? And we do those, right? We find power series for those and functions connected to them by a little sneaky trick. So let's just show you. If I ask you for the power series of 1 over 1 plus x, you should say, oh, that's just formula A. Okay. Let me do that again. If you do 1 minus x, you're going to say, oh, that is formula A. There we go. So far, so good. Now, if I integrate 1 over 1 minus x, right, which I could do, right? If I integrate that function, I can also integrate its power series. Does that seem reasonable? If a function is equal to its power series, then shouldn't the integral of that function be the same thing as the integral of its power series, right? And as long as your function is absolutely convergent, you are allowed to do this. Which is why, another reason why absolutely convergent is very useful, right? Now you might say, well, that's no good. I can't do that. Well, you could do this, which is also allowed. Instead of integrating a summation, you can summation of a lot of integrals, which is just a fancy way of saying, can you integrate each of these guys separately? So let's see what we get. If you integrate x to the power of n, right, where n could be 2, 3, 4, a million, the rule for integrating x to the n is add 1 to the power and divide by the new power. Would you agree? And technically, plus c. Now, let's go over here. If I asked you to integrate 1 over 1 minus x, you would get the natural log of 1 minus x. Agreed? Integrate that guy. What else would you get? Because there's a little minus x here. What else would I get outside? An extra negative. Great. If that was 2x, I'd get a half. So I have that guy. Can you trust me that if you plug x equals 0 in here, you get minus log of 1, which is nothing. And if you plug x equals 0 in here, you get a whole load of zeros, right? 0 to the power of this, 0 to the power of that, but still zeros. And that makes C 0. So what I now have is that guy. And he is sigma n equals 0 to infinity there. And I want to know what the power series of the natural log of 1 minus x is. And the answer is slightly ugly. I guess for emphasis, I'll put a little bracket around that. Isn't it just the minus of this power series? So in other words, do the power series and make everybody negative. So there is the power series for that guy. Okay, let's try it again. I want to take this guy as my starting point. And I know he is n equals 0 to infinity, negative 1 to the n, x to the n. And I will integrate him. And so I will integrate his power series. You can switch integration and sigmas and do them in the alternate order. So I'll do that guy of the integral of these guys. So instead of the integral of a sigma, I'm doing the sigma of an integral. Now the power series gets used. If you integrate negative 1 to the n, x to the n, that's just a number, so none happens, it's the same number. You add 1 to the power again, and you divide by the new power. Technically plus c, but for the same argument I gave earlier, c is 0, so don't worry about it. And what we have is this guy. And do you recognize this guy as the natural log of 1 plus x? So now I have a formula for not only the power series of the natural log of 1 minus x, which is this guy, I now have the power series for the natural log of 1 plus x. So I'm going to write them here, because I'll need them in a little while. N equals 0 to infinity, 1 plus x, negative 1 to the n, x to the n plus 1 over n plus 1. And this guy, n equals 0 to infinity, just a single n, x to the n plus 1 over n plus 1. And now I've got one more guy to find a power series for, the inverse tan of x. And I'm going to kind of work backwards here. Would you agree that the integral of 1 over 1 plus x squared is inverse tan of x plus c? You agree? Right. Now, my starting point is going to be that guy then, which means formula B. So he is going to be sigma n equals 0 to infinity, negative 1 to the n, but instead of x, I'll now use x squared to the n. And then make it look pretty. I'm now going to integrate this guy. which means he is equal to the integral of the power series. And then I switch the integration and sigma processes and do them in that order. And if you want to integrate this guy, it's a power rule. So everything else basically stays the way it was. That guy stays the same. Add 1 to the power and divide by the new power. Technically plus c, but the c's end up being 0 again, so I don't worry about them. This guy is the inverse time. And there we go. We now know the power series for the inverse time. So it's n equals 0, infinity, -1 to the n, x to the 2n plus 1. Should have given ourselves more room here. 2n plus 1. So if you can find a function that when you integrate it gives you something interesting, and that function that you integrate is in this family A or B, you can find the power series for the log of 1 plus x, the natural log of 1 minus x, and inverse tan of x. And then you take it one stage further. You do a question where you use these guys that we've already found to find the power series of, well, take an example, question 5. And in question 5, you have the function.
You wouldn't be offended if I asked you to slow down just a little bit?
No, I would never be offended.
Just because I'm trying to keep up and I'm not doing it, so I apologize.
I hear you. So while we're kind of getting down here, we have got 3 functions that we now know the power series for. A log of 1 plus x, a log of 1 minus x, and the inverse tan of x. And we are trying to find the power series for what originally looks like an impossible question. That does not look like any fraction you know how to do, because we only have 2 fractions. But we can do it. We just have to take it a little bit at a time. First thing I'm going to notice is that this inverse tan of x cubed, I know the formula for the inverse tan of x, so I'll write it down again a little bit big. The inverse tan of x is sigma n equals 0 to infinity is that guy. Now, if I know a formula for the inverse tan of x, if I know its power series, which I do, I can find the power series for the inverse tan of x cubed. What do you think I'm going to change this x here into to get the inverse tan of x cubed? Because that's the only thing I'm going to change. So this is for anybody. What am I going to replace that x by?
It's the x to the 2n plus 4.
I'm not sure where the 2n plus 4 is coming from.
Oh, because I thought that if you had x to the cube, then you would add 3, but I guess add 2 would be more like it, unless I'm completely wrong.
Well, I don't know. Are you just thinking of basically making that guy there x cubed and then multiplying it out?
That's what I thought of, yeah.
And that's exactly what it was. Just the way you said it kind of distracted me. Right, so it's x
Oh,
cubed.
okay, yeah, I
right?
explained it wrong. Okay.
Right? No, just I didn't hear it right. Right, so we have an x cubed here. Do you see that that becomes an x cubed? If this was x squared, wouldn't this become x squared, right? You could pretty much do it with anything you like. So we now have n equals 0 to infinity. That guy. X cubed raised to that is really messy, but essentially 3 times that. Right, so 3 times this guy gets you that, and there is your answer to the inverse tan of x cubed. It's this power series. And if that's all we wanted, we're finished. But we want to know what x squared, the inverse tan of x cubed is. We want to find x squared of its power series. I know what the inverse tan of x cubed is. It's this ugly guy. And I got this by using the formula for the inverse tan, which we found, replacing this x by x cubed, and then just tidying up. Now I want to add in one last piece. I want an x squared here. Right? So x squared, the inverse tan of x cubed, becomes x squared times its power series. And we know how to bring x squareds inside sigmas. All the guys that have nothing to do with x don't change. This guy gets an extra 2. An extra 2 just means you bump it up to, instead of 6n plus 3, you bump it up to 6n plus 3 plus 2 more, so 6n plus 5. So we now have the beginnings of a process for finding power series of functions. In this case, we've figured out a sneaky way of getting the power series of x squared inverse tan of x cubed. Kind of sneaky. And that was what? That's a version of question 5. Let's look at question 4. In question 4, they want us to find the natural log of 3 minus x. They want us to find the power series of the natural log of 3 minus x. And that is not nice. Great. Now, what do I have to work with? Well, I would start with this guy. And this guy becomes that guy. Okay. And I am going to find the power series for 1 over 3 minus x, because once I know that power series, can't I use this integration technique that we've done before? So start with 1 over 3 minus x, write it down in a format that's going to work. Thomas, can you hear me? Don't know. Yes, he can. Okay. Okay, throwing you in the deep end, Thomas. Are you ready for this? Which one of these two, A or B, should I use to get this power series? And let's see what Thomas says. And he says A, which is correct. And in this case then, the power series says whatever is here, where my finger is, right, which in this case is x, but in this case is what 1/3, goes inside here. And then we make it look pretty. So it's going to be, how's the speed going? Or am I still too fast, John?
No, it's okay. Thank you.
A little bit slower would be better.
No, I don't want to bore the rest of the class. I'll
I
watch
don't
it
think
again.
you're bored. Okay. So 1/3 to the n, x to the n. And then if you bring in the 1/3, join it to the guy that's there, so you get an extra one, x to the n. And then to make WebAssign happy, I just had a thought here. This version might be the one that WebAssign doesn't like, and it wants this one. What would be really nice is if WebAssign was happy with either, right? That would be the best scenario. Any questions about the power series for this fraction? Are you comfortable about the process that led to it? Anything that's not making sense yet? Okay. Now, we know what this guy is. Is this guy. That's his power series. You may have forgotten, because it's a long time ago, what we were trying to find was a power series for this fella. Well, first we got this guy. And then we realized that if we integrated it, we would get the natural log of 3 minus x times a -1. And this can be switched. So we'll do a sigma of an integral. So instead of an integral of a summation, we do a summation of individual integrals. And that essentially is how we can get the power series, because add 1 to the power and then divide by the new power. So add 1 to the power and then divide by the new power. Technically, with a plus c, take the negative of everybody technically we're plus c. That plus c you have been given. When you look at the question, it looks like this. The natural log of 3, take away, and it even gives you the sigma, and it looks like it starts at 1, not 0, but that's fine. I can do that without any hassle. I mean, if they want to start at 4, I'll start at 4. And we have this guy. And if you're wondering where does this log 3 that's sticking out like a sore thumb comes from, if you plug x equals 0 here, don't you get log 3? If you plug 0 in here, these polynomials are all various powers of x's. Nothing cubed, nothing squared, nothing to the 10, whatever it might be. All of those disappear, which means the log of 3 has to be c. So that's what that is. And there's the minus. Sneaky, but at least it allows us to find power series of various logs. That's good.
So it appears like the only thing that really changed from the natural log of 1 minus x power series is just the 3 to the n plus 1 and a negative sign in front.
Yep,
But then you
pretty
have the
much.
negative, you actually have the negative sign.
So I only need the 3. Right? If you
So-
did that, you could make a prediction. Let's do what you're talking about, John. I like that thought. If somebody asked me to do that, and I don't want to do all that stuff again, right? You could make a good prediction. Would you agree it's probably going to be log 4? It's going to have a minus because they all have a minus. They're all going to have the n plus 1, right? And the n plus 1, right? They're all going to have that. Wouldn't this guy just be a 4 now?
Yep.
That makes sense. If you find a pattern, which is what math, one of the things about math is, it's the study of patterns. If you can find a pattern, can't you then say, oh, hey, I can find the log of 20 minus x and 32 minus x and 4 minus x and any other minus x? Because once I know what happens here, I can adapt it to a 4, to a 5. Can I even have a half if I wanted, a half minus x, if I was being really weird about it? And I also, couldn't I do 3 minus x squared? Because if I did 3 minus x squared, wouldn't I just replace this x with an x squared and I get that power series? So if you've got one guy that you know the power series for, can't you do any substitution you like and adapt that answer to accommodate the new version of the question? Kind of cool. Right.
Oh, so one sec. Where did you get the ln 3 again?
They gave us it in the question, but if they didn't give you it in the question, plug x equals 0 on this side, and you will get the natural log of 3. If you make x 0 here, can you trust me, all you get is various powers of 0. 0 cubed, 0 squared, 0, 4, 0, 5. A whole load of zeros add up to 0. So on this side, you get a 0 plus c. That makes c log 3. So that's essentially the arbitrary constant c. That's where it came from.
Okay.
But in the
Yeah.
question, they actually told you it was that, so you didn't need to. In the previous ones that we had, didn't I just say c ends up being 0, which it did. So we didn't need to worry about it.
Cool. Thank you.
Right, now we're moving to some, I don't think difficult, I think it's just different. We are going to, I try to find the damn thing if I can. Where are you? Was it? Oh, here we go. This is a version of question 6. And we're being asked to find the power series for that integral. Many integrals are impossible to do, right? If I just said to you in Calc 2, integrate that guy, you'd probably say, well, it's probably a substitution. Can you trust me that there's no substitution in the world that will save you, right? T over 1 minus t squared is not going to play well with any substitution. Well, maybe it's a weird x sub. No, it's not. That doesn't save you. Maybe it's integration by parts. Again, no. There are just some integrals that cannot be done, right? They're just impossible to do. So what do you do in science if you want to find the integral of something but you can't integrate it? Well, what you can do is find its power series, which is possible, and integrate that power series to get the power series of your integral. And then if you want to know what the integral is equal to, couldn't you just add the first 10 terms together? And that would get you. You'd also be able to sketch it, couldn't you? At least if you sketch the first 10 terms, wouldn't you even get an idea of what the integral curve looks like? And there are some functions in mathematics that are described in terms of power series, right? They just say this function is the following power series. So there's a function called the Bessel function, which is an example of that. So step 1, find the power series. For this guy. Okay, it's T's, not X's, but that's not a big deal, right? Could be Y's or Z's if you like. Now, I'm looking at this guy and I'm already into the, you need to write it like that. Agreed? Hasn't it got to look like A or B? So I just pulled out the T times the 1 over guy that's left. Now, if that was T cubed, wouldn't it just be T cubed, that guy, right? So I could do that. Now, this one's open to anybody. A or B, which one do you use with this kind of fraction?
A.
Are we getting good at picking the A's and the B's now? You know, there's a kind of look to the ones that use A and there's a different look for the ones that use B. So this is going to be T sigma n equals 0 to infinity. And what about this guy here? Well, when it was in X, you put an X here. When it's T to the 9, you put a T to the 9 here. Are you comfortable about that guy there going inside? Right? You've seen a few of those now. Now, make it look pretty. T to the 9th raised to, you get T to the 9n. Okay, throw this one open to John. John, you like algebra. What will happen when that T comes inside? What's the new power of T?
9 plus 1.
Agreed? Now, step 1 then is find the power series. Done it. Step 2. Integrate the power series. Well, the integral of this guy, which is what we're trying to find, is the integral of its power series. Right? You can switch the summation to sigma and the integral. And do them in a different order. Add 1 to the power. Oh, anybody, what's the new power if you add 1 to this guy? What's the new power of T if you add 1 to it? It's an open to anybody one. What does that guy get you?
It's going to be 9n plus 2.
That's it. So, I've already got the 9. 9n plus 2. So add 1 to the power and divide by the new power. Agreed? Oh, that's actually as good as that answer's going to get. Well, plus a C.
Oh, there's no chain rule there.
You're saying chain rule. I'm not sure where you're coming, what you're coming from.
Oh, because of the 9n.
No, it's just, that's just 9n plus 1 is basically a constant, right? It's just a number. So you add 1 to
Oh.
the number and then you divide by the new number, right?
Oh, because you're not integrating with respect to n.
No,
That's
I'm
why.
integrating with respect to t. Yeah.
Oh, is that the reason, or was I?
Yes, that's the reason.
Okay, gotcha.
I mean, if we turned these all into x's, it'd probably be a little bit more familiar to you, right? But it is the same as the other ones we've done. So I can find essentially any integral I want as long as it's a fraction, right? So I can do 2t over 1 plus t squared, or 5x over 7 plus x squared, right? I could do all those integrals as power series at least.
If we were doing the chain rule, wouldn't we be doing differentiation?
If you were doing the chain rule, there's a chain rule in integration as well. So a chain rule in integration would look something like this. If I went and said to you, integrate that guy. Well, integrate a sine, you get negative a cosine times a half. That process of this extra a half is essentially it's a chain rule. Now, the normal process for chain rules would be, things like that, and you differentiate them. That's also called a chain rule. But in this case, you'd multiply by the power, reduce the power by 1, and then finish with the derivative of what's inside. I've made the inside quite nice. It's just 2. So you'd end up with that as your answer. But normally when we talk about the chain rule, we talk about it in differentiation. But technically, that's a chain rule as well. It's just different.
Thank you for the clarification.
Not a problem. Okay. How are we looking? Let's see. Have we done these guys? Yes, we have.
These classes have like a constant backpedaling. You always have to go back and.
Oh, well, you have to remind yourselves of stuff that you picked up like a year ago or whenever, right? Oh, God, yeah, I have to remember to differentiate this, or I have to remember U subs, right? It's full of little, you don't know what's going to happen, right? Anything could happen. Not talking about differentiation.
It's almost like a horror film.
Did you say a horror film?
Yeah, like, somebody could jump out at the corner and
Oh, yeah, you open the door and differentiation jumps out and bites you, right? Or factoring suddenly drops from the roof and hits you in the head. Is that your analogy right now, John?
yes, thank you.
So what does Dracula do? Is he integration and he sucks all your blood out? Or is that power series? Okay. Imagine I give you a power series. And this one is a version of question 8. So it's x to the n over n squared. And n equals 1 to infinity, right? So that's fine. And we are going to differentiate. Right, so we've taken power series and integrated them. What we haven't done yet is differentiate them. So we are going to find the power series for the derivative of this function, this power series, right? So here goes. If you want to differentiate a power series, does it seem reasonable that what you do is you differentiate the individual terms? Does that seem reasonable? So what do? You differentiate this guy. Right, now let's do that at the side. If I said to you, y is x to the n over n squared, and you have to think of n as just a number, right, a constant, then won't its derivative be multiply by the power and reduce the power by 1? Would you agree? Multiply by the power, which is n, and reduce that power by 1, right? And the n squared in the bottom. So n's are just numbers. It's like if I went and said to you, I don't know, x to the 5 over the number 5 squared, and I said you differentiate that, wouldn't you go 5 times x to the 4, and you still have it over 5 squared, right? Because that's just a number. Isn't that essentially what I'm doing here? Now, what does this simplify down to? Because you can do a little simplification. Is there anything on the top that might cancel with something on the bottom? This is for anybody.
Doesn't the 2 pull up? No. Yeah, the 2, there's a negative, there's a 1 over the n, so that is going to be into the first, so just be n, excuse me.
I agree. Won't the n and the n squared cancel and you get an n in the bottom? So I hope that's what you were meaning, John, right?
Yeah.
So that's what you get. Right, an n on the top cancelling with an n squared in the bottom leaves me with an n. Right. So
And it was hard to say.
yeah, I got the gist of what you're saying. So in this question here, if you differentiate it, you get n times x to the n minus 1 over n squared, just like we did a few seconds ago. That in turn becomes x to the n minus 1 over n. And I did a little thing there that doesn't seem obvious, but I had to do it.
You changed 1 to 2.
Yeah. And you might say, why do you change from n equals 1 to n equals 2? In general, when you differentiate a function, doesn't the first term, which is a number, disappear? So if the first term was 7, it's gone. But if it was 47, it's also gone, right? If you didn't change, basically that n equals 2 is saying the first term is 0 now. So I don't care what it used to be, it's gone. And so you do that. Now, if you wanted to find the second derivative, so basically when you differentiate somebody, will you remove the last term and start 1 up? So where do you think I'm going to start with this next one? Okay. Now, what's going to happen to this fella? Well, you're going to multiply by the power, and then you're going to reduce the power by 1. Now, do you see in this question, nobody got hurt, right? There was no cancelling. Now, if I did not keep changing this guy, right? If I didn't change this guy, and I made this guy 1, and then I made this guy 1 as well, what's going to happen when you plug 1 in here? You're going to have x to the power of -1, aren't you? And that should never happen, shouldn't it? Power series are always x's, x squareds. Right. So by adding 1 each time you do it, do you see you avoid that issue? Basically, you're saying, I know the first term is going to disappear to 0. Since I don't need the first term, in this case, the first term was n equals 1, can't I now start at n equals 2? And that takes care of any weird powers of x that might be floating about. Now, if I differentiate that, the first term's going to disappear. So why don't I start at n equals 3, right? If the first term's going to go away, I don't want it. And that will keep everybody else good. So it's just a rule of the process. When you integrate, you don't need to do that. Because when you integrate a number like 5, don't you get 5x? It doesn't disappear, right? It just gets an x attached to it. So integration doesn't need this little tweak. Now, in each one of these questions, I wish the question had been, tell me what they're equal to. But that's not what they ask you to do. They ask you to find the interval of convergence. So let me just tell you what the answers are. This one is -1 to 1. this one is -1 to 1 curved, and this one is -1 to 1. As you start, here you can use both endpoints. Right. Here you can only use -1, and here you can't use either the -1 and 1. So that's the 3 answers for 8. If you want to do them from scratch, that's fine. You'll use the ratio test and you'll find the 2 endpoints are going to be 1 and -1. You then plug them in and see what happens. So
Well, what's the
I-
difference between your first derivative and your other first derivative?
oh, I shouldn't have kept on adding and I forgot. Add 1 to get 2, add 2 to get 3. In fact, I
There's only-
don't need that question because they didn't ask me for it. Oh, they did, darn it.
No, I think what happened was your first derivative, you explained it one extra time. So I think
That's it. So I'll just put the answers down again a little bit cleaner. The original function doesn't have a problem. You don't do anything to it, but its interval of convergence is that guy. The first derivative, which we did get, will start at 2. And that's the x to the n minus 1 over the n guy. And this fella has an interval of convergence that looks like that. And lastly, the one that we finished with, which is the second derivative guy. So you notice we went n equals 1, n equals 2, n equals 3. And this one had an n minus 1 and n minus 2 power all over an n. And for this last one, right, so that would be the 3 answers. And let me just show you on the screen the same thing. There. Can you see the first answer, the second answer, and the third one, right?